Okay, welcome to 6502 Emulator in Python Part 17 with Tokyo EdTech. That is me. If you've been following along from the beginning, I know it's been a bit of a gap since my last video. I've been kind of sick, nothing serious, but just, flu, COVID, who knows, off and on for the past couple weeks. So you can probably still hear it in my voice. Anyway, let's get started. Today, we're going to be taking a look at the bit instruction, which is very similar to AND. It just has like one important difference that I know of. And then we're also going to try and create the addressing modes for indirect X and indirect Y. And they are a little bit different. And you'll see that today. So let's go ahead and get started. I'm not going to do any testing code today. Sorry, I just didn't have time to put it together. And I just really wanted to get back on the horse and ride here. So let's go ahead and take a look at bit. So I'm going to go ahead and I think I have it up here. So it says here, it's very similar to the AND command, which we've already done. So the main difference is that the AND instruction performs a bitwise AND with the accumulator and stores the result back in the accumulator, while the bit instruction performs a bitwise AND with the accumulator, but does not store the result. It's just used to set the processor flags. So basically what that tells me is I can just copy the bit command and yeah, I can just copy it and just make a couple changes. Again, I'm not going to do any testing code, just not in the mood, I guess you'd say. So let's go ahead and find the AND command here. And so I'm just going to go ahead and just copy this. And I think, again, there's still some of the flag stuff is still missing, but let's just go ahead and live with it. So I'm going to do bit. And so basically what we're doing is we're going to still get the value like we did before. And we need to do the AND. Now in the previous version, this was compared to the accumulator, which we're still doing, but the result was stored back in the accumulator. So I'm just going to go ahead and put a temp variable there. And then we set the N and Z flags based on that. So that should be all I have to do. Now, if I was looking back at the description here, it says I'm setting the NV and Z flags. So I think I'm only setting the N and Z flags. I'm going to deal with that some other day. Again, just trying to move forward here and trying to push through this last part of the of this this project that I've been kind of got a little derailed on, so I do apologize. Reasonably confident this would work. Don't know until I test it. But let's just go ahead and make sure we throw that in there somewhere. So let's find the bit command. And it only has 2 modes, so I guess we can just go ahead and just throw that in there quick. Let's see here. So let's go up to our commands. Scroll up instead of that. Yeah. So let's just go ahead and plop this in here and doop. And so we're going to go ahead and copy that. And we're going to paste that twice. So this one is 44. This one is going to be bit. And the mode is 0 page. All right, 0 page. And the second one is 2C. And this is also going to be bit. And the mode here is absolute. So that's really all we need to do to implement bit. Again, I know the V flag is missing. We're going to just come back to that some other day. I'm just going to be confident. I'm going to hit compile at least, see if it compiles. I'm going to call that a win. So yeah, feel free to play around with that. And if you see any problems, let me know. The next part I think is a little bit more interesting, is the addressing mode. So we're doing indirect X and indirect Y. And they are a little bit different, at least based on what I've been able to find. So let's go ahead and take a look at the description. And I found a really good description here on this website, Masswork, and it has a really good explanation of it. So basically what it is, it's very similar to 0 page X. But because it's indirect, it's similar to the indirect mode actually, but it's like indirect 0 page X, if you can think of it that way. So this instruction here, this chart here is really great. So let's say we have LDA $70X. Okay, so this is a 2-byte instruction, so it's only going to work with 0 page. So that's 0 to 255, the first area of memory. So in this example, we have A1, which is going to be the opcode for LDA indirect X. And then the value is 70. That's the memory location. And in this particular example, X is 5. So what we do is we add 5 to 70. That gives us 75. Then we take the value of the bytes that are at that location. So remember, it is, the most significant byte is second, least significant byte is first. So the memory location is 3023. It takes the value in that memory location and adds it to the accumulator, in this case LDA. But the point is the value comes from the location plus X. Look that up, get the data, and put that into whatever we're going to do with it. So the value comes from here. So let's go ahead and see if we can implement that. So first thing we got to do is create the mode here. So I'm going to do indirect X equals auto. I'm just going to do indirect Y while I'm at it, just since I'm here, so I don't have to keep jumping around. So we're going to do that one next. And then I'm going to scroll down. And in my get location by mode, let's see here. Okay, get location. So this is going to give us the location of where that is found. So we're going to do elif mode equals mode dot indirect X. So the location, okay, so I'm just going to go ahead and copy this because I think this is going to help us. So location is going to be location. Yeah, we're going to need that actually because that's indirect. Actually, that's not the. Okay, we're going to go jump back here. So let's go ahead and. How's this going to work? C+1. Yeah. Okay. So I'm going to use the 0 page. Actually, I can just use 0 page X here because it's basically the same thing. So I'm going to do the least significant byte is self memory self PC but +1. Okay. Now it's 0 page, so I don't really have to do anything else. And then again, I'm going to add. Same thing here. I'm going to add the X to that. Now, in the 0 page X, we would just get the value. That would be the memory location. Okay. However, actually, this is not quite right. Okay, got it. I think plus X. Okay, the MSB would equal L self.memory self.pc +1 plus, actually +2. No. +1 +1. Okay, I think that's right. I'll explain this in a second. So then the location is going to be this thing. Okay, the location. And then that's where the jump address is. So it looks very similar to this. So I think that's +1 +1. Yeah. Yeah, that's correct. And then the jump, I can just call this. So this is not the jump, it's going to be the location. So now, yeah. So now we're going to change it to that second set. Yeah, that's it. Okay, we're done. Yeah. Wow, that's pretty funky. So let me explain that now that I think I figured it out. So if you remember, let's take a look at indirect. So this is where we're jumping to a memory location that's stored in another memory location. So our least significant byte comes from, where the instruction is +1. That tells us the memory block that's going to be in. And then self-dump memory. Yeah. But in this case, it's in the same section of the code. But what this does is it tells us, so we're going to get the 1. So in the case, it was 70 in the example. And then it's 70 +1. No, it's 70 plus, it's going to be +2, I think. And I gotta think this one through here. We need, because it's 0 page. All right, so I'm gonna copy that again, and I should have done some testing code. Anyway, so it's self.memory, self-PC +1. And that's the location, because the most significant byte's going to be 0 because it's in the 0 page. Okay, I'll take that. Then the least significant bit of where we're going comes from this location, which would be 75 in the example, and then 76, which is that +1. Then we get the location, the new location, which is the real, which is stored in the memory, and then we go. I'm happy with that. I think that's correct. If anybody watching at home says, hey, that's wrong, let me know. Let's go ahead and try and do Y, which is a little bit different. You'll see the difference here in a second. So let's go back to here. I'm fairly certain this is going to work. I should have done some testing code, but like I said, I'm a little tired today. I apologize. So this is similar, except that we look up the address first, then we add the Y. Okay, so with indirect X, we were given location 70, we added 5, took the 2 bytes, so this would be 75, 76, and then we get the location from that. Or we get the location, then from there we get the, we get the data from that location. In the case of Y, and notice you can tell because of the way it's written. Here the X is inside the parentheses, so it's applied to the memory location. Here it's outside the parentheses, so it's applied to here, the lookup value. So if we get 3543, we add 10, that gives us 3553. And again, I know I'm not dealing with, kind of overflow stuff, but we'll deal with that's a problem for another day. So let's go ahead and just see if we can code that. So basically what I'm going to do is I'm just going to copy this because they're very, very similar. I should comment this better, but I had one of those days. So this should be Y, and so that gives us the memory location. And then, actually, that's not what we want. The Y doesn't go there. Once we get the location, we add the Y. Location plus equals Y. So we get the initial location. So that in the example here, what was it? It was 70 as well. And then from there, we get the least significant byte, the most significant byte. Transfer that to the relative, so that's the location of where that points to. That gives us this. And then we add Y to this location. And then that's it. Yeah, that's it. Command S or Control S, see if it compiles. It's a good sign. Again, I haven't done any testing code, but I think this is pretty close to what we want. Let's just go back real quick and see if we can find a command or two that has that. Sorry, an instruction. I know I was chastised for using command, but an instruction that has indirect X. So does LDA have that? That's always a good one to play with. Yeah. So let's go ahead and just implement the LDA version of this, and then we'll call it a day. Okay, so where's our LDAs at? There we go. So let's go ahead and pop that in there. I'm going to go ahead and copy this a couple times. And again, I know I should do some testing code, but it's just not in the cards today. Again, I apologize. 44. Nope, sorry, it should be A1, excuse me. A1 and B1. And this should be, I didn't mess it up. I want to indirect X, indirect Y. Yeah, I'm thinking about doing a whole video on just testing this thing, but haven't quite decided yet how far I'm going to go with that. We'll see. So I'm not super concerned about the testing. So yeah, that should do it. Again, let's see if it compiles. That's a good sign. I'm going to go back down here, make sure I didn't mess this up. Bit things. Let's go back and see if we can find bit again. So it's 24 and 2C, because I think I used 44. 24 and 2C. I should have known they're so different. Okay. So those of you watching home that were like, probably like, dude, you just messed that up. Yeah, I caught that hopefully here at the end. Again, there's going to be a lot of like testing and verifying that this is doing what it's supposed to. Yeah, that's a big project in and of itself. Something I didn't think about when I started this. So going back to coding concepts, what we did was we implemented bit, which is very similar to and, so I was able to just copy and paste that code and just make the change where we didn't store the value into the accumulator. And again, I know I got to go back and do the V flag, I think it was, but yeah, that's a problem for another day. And then the addressing modes, we talked about indirect X and indirect Y. Again, X is added before you get the data of the jump address, or get the address that the indirect address you're referring to. And then in the case of Y, you get the address and then you add the Y to it. So, the X, in X, it's applied to the 0 page location. In Y, it's applied to the location that's returned from the data that's in the 0 page, if that makes sense. So, yeah, thanks for watching. And as I like to say, keep on coding.